Herkese merhabalar.
Öncelikle there is loss of heat, and here there is no we are trying to come up with the awareness raising. There are the heat losses. For example, 10% of this. And if it is condensate, it is 99% efficient.
Then we have loss of heat. As regards to the fundamental concepts, we need to recover and correct some misconcepts, because this heat and also thermal heat is confusing, because sometimes they call it heat. When we call it heat, when we call it thermal, it is energy. And we have this physical one and we can measure it, we can feel it. As regards to the heat, it is mainly the intuitive. We just feel, and we do not have, for example, thermal. We do not have this heat at this level, etc. So it's mainly the measurement of this issue. For example, vapor, solid, and also this issue, and there is a balance, and we call it 0.1 Celsius, and it is 273.16. That is our scale. Sometimes it's called centigrade. Centigrade is based on cent. In the past, 0 is the point of the freeze, and we have the centigrades. Now we use Celsius. So the official and the correct name is Celsius. And we have, of course, the location of energy. So nothing disappears while it is there, or nothing occurs if it is not, because there is no exception. No matter which machine that has, they cannot violate this rule. And as for the thermodynamic, is a discipline itself. What is the essence of it? While you work on it, the total energy and the net change in its total energy, and also the difference between the input and the output of energy. So the total energy that enters into the system, and we get the difference when we deduct it from the total input. This is so simple. So the energy that enters and the energy that we subtract, and then the energy that we have as an output, and then we get the difference. So if we want to have it rapid, we use the units version, and then we call it the input and the output. It might be in the form of energy or with the mass, and then it is equal to the energy within the system, and it is equal to the and we can see it in the scheme. Energy, of course, the simple way is thermal energy. We have energy within the building or within air, then if it is too much, then we feel hot. If it is enough, then we feel comfortable. And there is also this energy with some chemical energy or some hidden energy. When there is this chemical reaction, and we have these chemical reactions, so there is no change in the structure of atoms. For example, there is carbon or hydrogen, and while it burns, nothing happens to atoms or other materials. For example, if something happens to atom, and if it turns, for example, into helium, then we call it nuclear energy. So usually, this is not our topic for today. the issue that we will talk about is the thermal energy or heat. It's mainly about the movement of atoms or molecules. So it is the reflection of the movement. So we see increase in heat when there's an increase in their movement. Another important point is the efficiency. And we have this, we want to achieve something, and then we do something in this respect. It is the productivity that we are dealing with. For example, we want to cook something and we want to cook pasta. That means we need to boil water. Of course, it is not easy that it boils itself within the temperature of the kitchen. That means we need to burn something, or we will transform electricity into energy so that it will enter into water and then it boils. For example, we have a device, heater with 5 kilowatt, and then 3 kilowatt enters into water and the 2 kilowatt goes to the kitchen. That means the efficiency is 60%. This is the efficiency. As you see from the table, when we cook, for example, efficiency changes a lot. For example, you can use different energy. If you use a stove with electricity, it is 2 kilowatt. But if it is microwave stove, it is 0.36 kilowatt per hour. It is like 1 out of 5 or 6 out of 1. So if you are going to make coffee, then you can consume less energy. This is the efficiency. And as regards to lightning, we will talk about this issue. For example, we have this energy efficiency lighting. While we use the same bulb for the lamps with white heat, and it is 6 to 20, but if it is in the solid, it is 20 to 160. We call it energy efficiency lighting. And we, comparing to white heat, we can save up to 80%. So rather than paying 100, you can pay only 20 Turkish lira. Oh, and also let's talk about the cost efficiency. And rather than the energy amounts, if you pay attention to amount of money that you are spending, it is economy. In fact, it is quite equal to each other, and it's one of the equal. So people usually ask which type of heating source is more efficient. I have a publication on this issue that was published 2 years ago, and I compared natural gas and also LPG. 2 years ago, 1 unit of the natural gas was 1.8 TL and LPG was 108 TL, but their unit was not same. And you see their value, and what we see that 50% of efficiency. That means 50% is lost. If it is electricity, it is up to 75, but if it is induction electricity, then it is 90%. So the money spent for heating, it is 44, and LPG, it is 159. If it's electricity, it is 98, and if it is induction, then it is 90. It's 81. So, of course, it changes according to the price, but if you have natural gas, for example, it is useful to use it and helpful. And if you use electricity, then you pay twice. Comparing natural gas, comparing LPG, if you use a stove with induction, then you save money. So it is about economy, and you can calculate this issue easily. Sometimes simple calculation is extremely important. For example, lighting cost. You don't need to be an engineer. You can make calculation. It's a simple example. If in an example there are 30 bulbs and these are 80 kilowatts, and all these lamps is with fluorescence, and then you can easily calculate what we need to pay attention. There are 30s and they are all 80 watts. That means when we multiply them, it is 2,400 kilowatt. That means 2.4 kilowatts. And given the fact that we use them for 250 days, you can simplify it, and it is 3,000 hours per year. And energy is about using this issue. And when we multiply 2.4 kilowatt, multiply 3,000, then it is 7,200 kilowatt per hour. It is important because we use kilowatt hour as our energy unit. And when we multiply it, then we get this kilowatt hour. Kilowatt is the energy unit, and we have this kilowatt for this. For example, our distribution generates 5,000 kilowatt. But when we talk about power, we use kilowatt. But when we talk about energy, it is kilowatt hour. So if 1 kilowatt is in for 1 hour, then we use kilowatt hour. It is confusing sometimes, especially in Turkey. In total, we have 7,200 kilowatt hour, and then we have this cost, and it's 0.70 cent. That means it is 504 US dollars, and it costs a lot for one classroom. It's a normal one, so it is 5,000 Turkish lira, about 5,000 Turkish lira. So this is why efficient lighting is important, and some of my colleagues will talk about this issue much more and in a detailed way. Another issue that we need to pay attention is the air pollution resulting from energy. And when we use all these chemical reactions, what we have? We have carbon dioxides, etc. And also hydrocarbons which are not burned, or carbon dioxides, etc. All these issues are related to energy, because if we use this energy, that means it is less pollution. But if we use fossil oils, then we move away from this issue. As we see in this photograph, our lungs are exposed to pollution, and it is not good for our health or our economy, our budget. And it is the CO2, green gases, and they form a cloud which makes an impact of a greenhouse. And it's an interesting info. A car generates CO2. which is much more than the weight of the car itself. Another issue is this, as you all know, it is specific heat and the required amount of energy to increase 1 Celsius degree. For example, if we want to cool down a Coke, what we just need to do is we just change in its energy and we just multiply it, and then we achieve this. And then, so it is about the energy transfer from the Coke. We need to remove this energy from Coke, and the energy balance here, especially for this energy transfer, it is the energy that enters and the energy that leaves, and then the difference. And it is not generating energy. It is in this case, it is the energy lighting, or if there is any electricity heating, or it's the energy production. What we have here, it is about the change in its thermal energy. This is the main formulation that we have. And this is the main equation that we have here. As regards to the surface energy, as you know, surface energy does not store energy. So the surface energy needs to be equal to the energy and the energy that enters and the energy that leaves. And so it must be equal. So let's look at a wall. For example, it is the interior wall, let's say, and we lose energy, and then we have this Q1, and then as we will talk, we will receive it. We will lose it later, and then there will be 2 mechanisms. And then we see how it moves, because air carries this heat. So Q1 equal to Q2 plus Q3. That is radiation. This is the energy balance that we are using. I also would like to say we will have some breaks. So if you have questions, you can use the chat box to send your questions to me. I can answer your questions at any time, or I can answer all of them at the end of my lecture. Following this general overview, let's move to the heat transfer. There are 3 mechanisms. Heat transfer, and we have this conduction, convection, and radiation. So we have this conduction, convection, and radiation. These are the English terms, so you can use whichever you wish. In this image, as you see, this part, the red part, is radiation. Even though there is no connection, there is no touch. Then if there is this touch, then it becomes conduction. And if there is flame, then since it includes air movement, then it's convection. As for the conduction, if you touch this part of the plate, then you will feel this part, because sometimes it is parallel, sometimes one transforms into another. These are some, this is the second rule of thermodynamics, that is, heat moves to the part that is colder. So if it's 70 and the heat is 20, so if you leave it, heat leaves coffee and moves to the air. That means there is energy loss because 70 Celsius degree will reach 20. So we never say that it's 20 Celsius degree and let's expected coffee will be 80. No, that is not the rule. That is the main rule. The second issue is the difference between high heat, means high heat conductivity. So let's say the temperature within the room is 25 and the heat is, let's say it's a Coke and it's 25, then there is no difference. So there is no conductivity. But in order to have this, there is need for difference. If it is 50, then the difference is 10. Then let's say it is 8 joules per second. Then there will be difference and it is higher. Then the heat transfers in a faster way. It's like 16 joules per second. So the key concept is the difference between heat and also it is the driving force of the heat transfer, and the higher difference means the higher transfer. As regards to the main heat equity, it might be a wall or it might be a drink, as I said, and it might be 0.5 centimeter thickness, and let's say it's a wall, it's the interior heat, it is T1 and T2 as for the exterior heat, and there is this heat loss. And let's say this surface is A and the thickness is delta X, and there will be heat loss. It might be wall, it might be roof, windows, it might be a surface, or it might be a curve, and the principle is same. What we see that the heat difference, T1 deducted from T2, also becomes double. So if we have the thickness double, then the heat loss and the heat transfer becomes double too. But if the thickness is doubled, let's say we increase the thickness of the wall, then the heat transfer speed reduces to half. So the key concept of this heat transfer is the transfer is there is a oppositional direction with the thickness of the wall, and there's a direct opposition, direct proportion with all other values. And then we can use the equality. It is difficult. And for this, the heat transfer, and then we multiply it, the surface area, and then multiply the heat difference, and then we divide it into the thickness. And we can use it in transfer. In order to have the same direction, we can use minus, but these are not important details. So this, we need the conduction. This is the conduction, and we may need to have these messages. But let me stop here. There is a question here. So we are talking about you said there is this inverse proportion as regards to the thickness of the wall, and you said direct proportion with all other values. I think this equation indicates the importance of this issue. Let's say it is insulation. Let's consider it is an insulation plate, and we want to reduce the heat transfer. What we need to do, it is quite clear. The thickness of the insulation is important. If you make it double, then the heat transfer will be reduced to half. So the insulation is important, will reduce the amount of the heat transfer. For example, if it's an isolation, that will be a wall or some other elements that we will pay attention and that we will take into consideration. But the thickness of the insulation is important to prevent heat loss, or if it is summer, then it is the heat recovery. For example, in the summertime, if you are using an air conditioning for cooling purposes, and if the weather is hot outside, then it will prevent the energy entry, the heat entry into. So the thicker, the better. Another factor is that the number of floors, and what we have these coefficients here, and if it is copper 400, it is aluminum, it is about 200, and if you want to transfer it, you will use metal. But if you don't want to, if you want to prevent, then you will use, for example, glass wool. It is 0.4. You will use fiber, and air, it's 0.026. That means air is the best insulation material. And we have this solid foam, then we have all these best parts. For example, when we have a jacket with different layers, then we have, or the furs. All these are important and ideal insulation materials. So it prevents heat transfer and the heat loss. As you see from the table, the transmittability is very important. It might be foam, the wood, or fiber. And we have metal. So why do we use oil for our cook, not water? Because water boils much easier and shorter than water. Let's look at metals. We see their transmissibility is important.
It is 4 degrees. We said that 8% is for that. These are all we use the USD dollars. This is how it is translated. That's why I'm using that. So when you multiply cent with the 10, you can get the Turkish lira price. So let's say it is a night and 10 hours a night, and it's if these temperatures are fixed, we can say that what is the cost of the heat cost here. So there is a conductivity, and we use this system, and it is the conductivity is 0.8 Kelvin. And we see that the temperature is 15 minus 4, and it is the area is 6.848, and when we multiply it, it is 1.60 kilowatt. So if the ambient temperature is to be fixed, in order to compensate this heat, then it's 1.69 kilowatts heater should continue to work so that it can be compensated. There are also heat losses with the walls. We can say that we need 3 or 4 kilowatts of thing. And when we look at the roof, when we say kilowatt, it is a kilojoule per second. So it is the energy amount in unit time. When you multiply it, it is 16.9 kilowatts per hour. And when it is a kilowatt hour is 0.8. The dollar is when you multiply it, so $1.35 is the result. So as Turkish lira, when we multiply it with 10, it is 13 Turkish lira. So from that roof, there is a 0.25 meters of insulation. So we can say that there is a 10 to 15 Turkish lira. In order to have this, the insulation should be made. You have to be very diligent about this, but the calculations are very easy. When there is multi-layer, you have to have it as a systematic water. If there is wall, what should be the insulation? If there is convection here, or the conduction, or we say there are other things. So we are developing the concept of, for conduction, we already discussed this expression. And we will, as it's the case in electricity, there is voltage difference, right? And it is a V1 and V2. And there is also resistance of electricity. We get the proportion of this, and we get the current, the electricity current. In the heat, we want to do something similar. And instead of electricity, we see the conductivity, and the heat difference is the driving force, and there is the heat resistance. So we say T1 minus T2 divided by the resistance. So we can say that the resistance will be thickness divided by the conductivity multiplied by the surface area. So if we have this Ka here, we will we have the resistance, and we get this result. And also the convection and conduction, if we wanted it, the resistance, the heat transfer will be heat difference, let's say internal and external heat divided by the total resistance, as it is the case in the conduits of the electricity. So we can solve the problems very easily like that. And as you can see here, it is a 35 degrees ambient air is present, and when there is the wall, this decreases to 18%. There is the air movement, so we call it as convection. There could be other layers like insulation, and from the external wall, it is in this normal convection, and convection plus radiation. But we can look at them separately, or we can just gather them together, and we can have one heat transfer coefficient. Heat transfer can be solved in this way. So the ambient air minus the external air heat, and divided by resistance. So this is how we look at the conduction problems. So for example, in our building, let's say we want to have 5 centimeters of insulation. Well, how much it will be less for the heat transfer? So we can say that there are three things, and we will plus the thickness of the insulation and the conductivity, and the surface is the same, area is the same, and this how the heat transfer is present. For example, there's a single glaze window for the thickness is 8 millimeters. So the conductivity is 0.78, and the ambient air is 20 degrees. If there's one glaze window, single glaze window, we will talk about the heat transfer. But as it is a single glaze window, the convection here, and also there is conduction, and there is also a convection, and also there is the radiation coefficients. There are three resistances there. We know the heat, and therefore we look at ambient air and outer air, and divided by the resistance. This ratio will give me the we can say that the height of the window is 0.8 and the width is 1.5 meters. We will use these expressions for conduction, for convection. We can add these, and there is the total resistance, and we make this calculation, and there is 266 watts. So from this window, per second, there's a heat loss of 266 joule per every second. If we take into account, we can calculate the T1. What is the T1? Is 2.2. What does that mean? So here there's a single glaze, and minus 8 Celsius is the outer so of course there is a there will be the formation of a layer of icicle. There are some questions from YouTube, so if you want, we can just answer ask the questions. Figen R asks the question. There is the insulation material, and also wall, there is 5 centimeters of gap. I liked it, and however the master said that it is not very good. What do you think of this? There's the gap between the insulation layer and the wall. The air is the best insulation material, as I have pointed out. There is very good that there's air gap. I will show you the next example, then I will answer that question, because it is quite related to the subject. If there is the single glaze, there is a situation, as you know, it is forbidden to use the single glaze. So they use the double glazed windows, at least double glazed windows. So the question was very timely. For example, 8 units, let's say the 4 millimeters and 4 millimeters, there are 2 glasses, and there is 1 centimeter of air gap. All the trials show that if it is a 3-4 centimeters, the air movement is very small. It's almost non-existent. It is the same with insulation. So we can say that there is a 1 centimeter of insulation between 2 windows, because the conductivity of the air is very low. We can see that 0.026. However, for the glaze, it is 0.78. So we can say that the 2.6 is 278. You can see the difference. If we have double glaze, the heat transfer, what would be the case? It was 166. There is the resistance of the glaze and also the resistance of the wall, and with the simple calculations, this is the new resistance. However, there is 20 centigrade, centigrade and x minus 10 centigrade. What was it? It was 266 watts. So there is a 1 centimeter of air gap, and it decreased from 266 to the 96 watts. So it is a T1 plus minus 2%. Sometimes the glasses can be frozen. It was a -2, but it is now plus 14.2 centigrade. So what is double glaze? There are the two glasses. In between there is the air, and this is the same with the wall as well. When it is few centimeters, so you can use this one exactly. So there could be small conduction, but it is not very effective for the conduction approach is very valid here. So in the market, there are a lot of people who think that they know the best, but you have to know the fundamentals. This is the objective of this class, actually, this lecture, to give the fundamentals and to look at the questions accordingly. I guess I answered this question with the example of double glaze. There is one another question about insulation. It is related to conduction. So from the internal and external surfaces, so instead of insulating 20 centimeters externally, if there is 10 centimeter from internally, will that be create a difference? There will not be any difference. So at the end of the day, you look at the fundamentals. So for example, this is the insulation and this is a resistance. The resistance can be here or there and the calculation does not change. So actually, if we look at all the at all the resistances, but their place is not important. So on a normal life, so we prefer external wall. Why? Because when you put it into internal wall, let's say you are going to have a plate or you're going to have a screw, this will not be there. However, if there is this cement there or mortar there, it will be important. When you multiply it, generally there is insulation and is 1 centimeter of a gap, and in the US, sometimes people, they hit the wall and their hand is, enters into the wall. So we can say that it's about a sheetrock, and of course you have to put it this way in terms of thermal efficiency. There is no difference of this. If we are talking about the convection, and convection is conduction plus the fluid movement. So in the solid there isn't like convection, and if the fluid is fixed and without any motion, it's motionless, there is no convection. There is and therefore so we can say that there is the conduction, not convection. However, if there's a heat loss from the external world, there is a wind and other things outside, it is open for the movement. If there is the internal surface is very high, and if there is the convection, the air is moving inside. So we can say that in terms of the convection efficiency, for example, you're eating something very hot, you just blow it to cool it down. So we can say that it is 35 degrees, or let's say 37% Celsius, and ambient air is 25 degrees. So we can say that the meal is 80 Celsius degrees, and actually the heat difference is very high. So you can just leave it into the room, and it can be cooler, but we just blow it, because when we blow it, there is the air movement, and the air movement increases the heat transfer. So even if it is temperature is higher, we can say that this is on one hand it is you just cool it down more efficiently in a shorter period of time. So this is very important. The more movement, the more transfer and convection. Therefore, we use the fans for that. Why? In order to have the air movement. Normally, let's say there's a hot surface, and the hot surface, with that, the air will increase and it will expand. The air will expand, and what will be the intensity of the air? It will decrease. So, what is the situation? So there is a low intensity air, and there is the high intensity air that will increase. It is like the timber flowing on the water. It will swim up to the air. This is the leverage of the water, and we see what we'll have here. There will be there is the lifting force, and of course we look at this as a convection. This is a very complex, complicated issue. So what we do, we express it in a way. This is the convection heat transfer coefficient multiplied by the heat difference. This is the surface temperature, and we say T surface. And of course, this means infinity. Mathematics is not infinite, and it is away from the surface. Let's say 20 centimeters Celsius degrees. So we look at this, and when we this time we look at the proportion coefficient. We can see it there. And also, however, when you have the value, you can just directly use this. For example, in MATLAB, you see that there are the external walls. It is taken as a 20 for internal walls. So it's taken as a 10 as there's less air movement. And you can just find them in the manuals and handbooks. And the calculation is very simple. And if the cooling is not enough, we use fans. And why? Because it increases that air movement, and the cooling is even more. So it is like you blow to the meal. And for example, when you look at this hot, like we don't see the air movement, but however here, for example, if you look at this with a camera showing the intensities, you will see these movements. The air movement can be seen very easily. So this is the natural convection or the free convection. The natural convection is not only about air getting high, the air can get low as well. Let's say there is a cold Coke, cola, the air will get cooler, and there's air movement. So there will be a hot water in replacement of this. If the the cold water goes and the hot air comes, so we can say that the gain is higher. That this is the convection. As I pointed out, we see there is when we say H. H is the convection transfer coefficient for the gases. It is 2.2 and 25, and for it is a fluid 10 to 1000, and for the gases force convection 20 to 25, and it increases to 20,000 in there. And if there is boiling, it increases up to 100,000. So the phase, there's phase change. So even if there is a very low change, if there's a phase change, the heat transfer will be very high in the unit time. Therefore, we use fans when in the winter. Does it cool the air? No. So why do we use them? If it does not cool the air, this is because of them. For example, our body temperature is set, the ambient air is set, and also the surface is set as well. However, this is the heat transfer coefficient. When the coefficient increases up to 2, so we can double the heat loss, and this makes us feel better. So the heat transfer increases. And the same is used in the ovens. So let's say when we look at in the furnaces and ovens, we can see there's the first convection and transfer to the meals is very fast. This shows the propriety and characteristic of convection, whether the fan increases, cools or makes the air hot. What does the fan do? It takes the electrical energy, it turns into movement, and with the movement, then there is the that actually makes the air move, and then turns into uh, the heat. So if you're having a fan, this you have to cooling with fan. You have to open one or two windows. This is the same with the refrigerator. If it is in a closed environment, sometimes they put the refrigerators within the timbers, and it is I see that in the hotels, and the refrigerator will not make cooling there. It will work with very low efficiency because the refrigerator actually increases the heat in there. For example, the bulbs, light bulbs. If there is 100 watts of bulb, will give 100 watts of degree. It is, of course, in the winters, you have to give us such amount of heat. For example, here there is a 200 watts of fan, and the and here we can say the ambient air, to what extent it will increase the ambient air temperature. Of course, that will be imbalance, and when you use energy preservation in a steady manner, the important and exported energy, when they are equal to each other with this equation, you can say that the 25 degrees Celsius air, when it is 26 degrees, that will be there, and you can make it this factors, and also there's also wind chill factor. For example, outside in the winter, when there's a wind blows, so you get shivering, you can feel that wind. However, let's say if it is 5 degrees, and if there's a very good wind, that can be minus, we feel it like minus 11 Celsius degrees. This is an ASHRAE formula. We see the speed and the feel the temperature which is felt can be calculated. If there are questions, I can answer the questions. If not, we will continue with the third mechanism, which is radiation. We have a question. As we are in zero build forum, the buildings are more related to insulation. Uğur Ceylan asked, in some certain buildings, they use the coating with this stainless steel, and they put it's isoglass there. Would that increase the insulation? That's a good question. Actually, when you look at the fundamentals again, why I'm talking about the fundamentals only, because you can find answers right here. For example, let's look at the glass here. There are some resistances. Let's say this is the wall instead of air. So let's say let's put here a metal. Could be a copper metal, very conductive. 1-2 millimeters thick. The copper is very very conductive. So So it looks like it is very conductive, and there's a new layer of resistance. What is the resistance amount? This is the thickness of this copper layer divided by the same surface area, and also the conductivity of the copper. But if the K value is higher, you can say Ka is a positive figure. So the stainless steel or the copper layer as a resistance, and that actually heat transfer is decreased here. It doesn't increase, but decreases the this heat transfer. So we'll continue with radiation. We see radiation here with the X-rays. We just look at the X-rays. However, radiation is the electromagnetic wave. I use it with the same, and the thermal radiation is called radiation, and the radiation is responsible for heating our houses in zero buildings. You will see such applications. So there's maximum use of the sun, for example, even that part, and the size of it is very important. And if it is long, you can see it that there are the blue beams do not come inside, and it protects you from the sun in summer, and in winter it is the long air, and the sun will be there, and the sunrise has come here.
So in architecture, even these details with the right calculations make a difference. Here you see actually benefit from the solar energy in a passive way, and also get protected from its harmful effects in summer. And here there is this roof window. You can get direct sunlight, and this one protects you from sunlight during summer. By opening this window, you are able to enable the warmed up air to leave, and by placing solar panels, we are able to store that energy in the storage and then use it for other heating purposes. And by using low heat energy, thanks to the radiation energy, you're able to get warmed in a more comfortable and gradual way. So this is actually a use of thermal radiation in homes. However, a general evaluation would let us see that radiation is everywhere. Actually, we give thermal energy through radiation in our bodies, and almost 1/3 of the energy in our bodies. So this radiation does not just originate from sun. Even the ice uses energy through radiation. Furnitures, walls, plants, seats, and what is the net energy? Their difference. Here you see actually a chicken being cooked with radiation. I mean, here, as in the case of radios, the radiation is turned into electromagnetic wave, and that wave is arranged accordingly. So the wavelength in your mobile phone is not that different from this wavelength. And then it absorbs those formations and turns into heat. So it's sort of the preservation of energy. Here you see an electromagnetic spectrum, and the thermal radiation here actually can be located in this part. I mean, it's between 1 and 100. And then we have the actually another wavelength, which is infrared. And also we can see ultraviolet. And here you see the electromagnetic segment. And that's the difference between the heat and light. They are actually the same things, but what is the difference? Our eyes are receptive to wavelengths with this size. Actually, if it is 0.44, we perceive it as blue, and there's nothing like color. This is all perception. If it is 0.63, then we perceive it as red. If it is 1 micron, for example, we do not perceive it at all. Our eye is not sensitive to that. Other creatures might see actually the infrared, but we don't see that, and we don't call it light. And in this case, we use light by taking ourselves as a reference. And here there are different terminology. When a light comes from sun or another source, we refer to absorptivity. Here, this actually shows you the coefficient of reflectance. If we're talking about a glass component, then it's absorbed, and that is represented by alpha. And some other are conducted, and that's called TG. So here, actually, you see a calculation based on absorptivity and other factors, referring to energy protection. You see that if there is this opaque surface, reflection coefficient plus absorption would be equal to 1. So here, alpha times Q incoming means the absorbed amount. What is the greenhouse then? There is the greenhouse effect then. Here you see a glass. According to the wavelength, we look at the transmissibility of the, or conductivity of the glass. 0.3 and 0.7 is actually the visible light. And when you look at the conductivity of the glass, you see it's around 0.9. I mean, it depends on the thickness, but it conducts 90% of the incoming light. Here you see the infrared part. Starting with 3, the permeability or conductivity decreases radically as this light is absorbed. It doesn't let it to permeate. So an incoming light, as we know it, I mean, originating from sun, between, for example, 0.3 and 1, then it goes through it. If it is more than 1, and then actually it is absorbed. So glass is not a conductive material for infrared wavelengths, and we use it in greenhouses. Light goes through the greenhouse. It might be open plastic or glass. However, the heated plants, other substances, their warmth, let's say, is around 300 Kelvin. They're also giving radiation, but this radiation is has a long wavelength. So what does happen? It goes up, but it cannot actually permeate. It gets absorbed and comes back with a blanket effect. That's what is called the greenhouse effect. So you are able to achieve high heat. What happens when you leave your car outside in the sun? It's like hell when you open the door of your car. Very hot indeed. Or even if it is 25 degrees outside, it feels 35, 40, and even higher inside. What is the situation in the world with carbon dioxide and other emissions? Those wavelengths are actually insulated, and the Earth is prevented from getting colder. Here, absorptivity also changes depending on the wavelength it's set, and it leads to misunderstandings. For example, let's call this a cement surface, be it painted or not. The radiation coming from other buildings or clouds actually is absorbed at 90% because it has a short wavelength. And here it's around 3 to 5 micron. Sorry, he says it's long wavelength, but for sun, it is generally short wavelength, and it's 0.6 in cement, the absorptivity ratio. But if you don't want to absorb the sunlight, then you can paint it with white so that it gets reflected. So actually, you can decrease this amount to a huge extent. So actually, paint can be used to prevent such absorption. If you want to reflect it, you can use aluminum with good properties for short and long wavelength. That's why aluminum foil can be used for a fight against radiation. You don't want, for example, chicken to be cooked well in some parts, then you should cover it with folio. Why? Because it prevents the conductivity of such wavelengths. Again, I would like to point to a misunderstanding. We think that paints make a huge difference with white paint reflecting the radiation, while the black one absorbing it. That's correct. Regardless of its source, black absorbs radiation, but white paint reflects the sunlight, but it is not that different regarding the radiation coming from outside. So if you're inside the home, that doesn't make much a difference. But for walls that interact with sun, it makes a difference. When you look at the human body and human skin, you see that normal radiation, the long wavelength, is absorbed in all of it. But the people with white skin actually absorbs almost half of the sun coming from the radiation coming from the sun. How can we ensure insulation against thermal heating? Here there's this vacuum in the thermos, and they actually get the air from here. But does it end the heat transfer? No, because radiation does not need any area. So it is transmitted even through the vacuum, but the heat cannot be transferred. Can we also prevent that? Yes, with an extremely reflective surface, like a thin aluminum layer or silver layer. So here you evacuate the air on one hand and place a very reflective surface, silver or aluminum, we said. We actually ensure that the heat transfer is almost zero in flasks or thermoses. That's a very effective insulation method. As for the question, let's say we cover one surface of the wall with aluminum folio, it will have this same effect. It will cut the thermal conductivity resulting from the radiation as well. I don't know, it's generally preferred, but by doing this only, you actually prevent heat loss or heat gain in summer. If it's 5 degrees Celsius outside, if you're close enough to the fire, which is, let's say, around 1000 degrees, you get warmed very well. But you also need to turn your back, as it will not get that heat. How do we calculate it though? The radiation emitted actually is calculated as such. This is the fourth actually square of heat. And here Stephen Boltzmann constant is calculated to reach the ideal radiation. This emit calculation, or the coefficient of radiation, is somewhere between 0 and 1. And that's how a normal behavior acts with the radiation level, radiation coefficient. If it emits and receives and emits radiation, we should actually take this element of the equation outside. This is the surface area and Stephen Boltzmann constant, and this is the epsilon radiation coefficient, and then you see T times square. So actually it's an easy calculation. And here you generally see this element on the tables, and it's not difficult to find that coefficient. What about the total heat transfer? It can take place through transfer, Q transfer. So H T3 minus T8 plus radiation. And then here you see these phrases. Sometimes they are combined for the sake of ease, and they are written like a conductivity, but that H is not calculated for radiation. So I think this one also attracted your attention. In milk containing tank containers, they have this actually bright surfaces. They have polyurethane and insulation in the inside, but when you place this, all the sunlight is reflected back, and the radiation coming from the clouds and such are also reflected. So it's very effective. Otherwise, you wouldn't have a bright surface. If you paint it with white, it would reflect the sunlight, but not the light coming from outside. And that would not preserve milk significantly. What about the effect of radiation on comfort? We generally check the room temperature. Let's say the room temperature is this much, and it will lead to this value. For example, it's 22 or whatever, but the surface heats also impact our comfort. A human body has let's say an average surface heat of 30 degrees. You may ask why not 37? Because it's the inside temperature in human body. It should be 30, 31, 32, 33. Otherwise, we cannot emit heat. And here you see the heat on the walls. Let's say it's 10 in winter and 25 in summer. With radiation, this person actually transfers heat. We place the formula elements here. Actually, when the walls have 10 degrees, the person loses 152. When the walls have 25 degrees Celsius temperature, that value comes down to 40.9 for humans. So this thermal radiation has an impact on the comfort. That's why, as in the example of double glazing, actually has an impact. The degree difference increased from 2 to 14, as you remember. That also applies to walls, and that provides thermal comfort. I mean, you check the boiler, it's 24, 25 degrees. You say, I should not feel cold in winter, but there's this wall impact. As for parallel thermal transfer mechanisms, in the solids, there's just conductivity, and gases, there's radiation, and here it can be conductivity and transfer. Or if there's vacuum, then there is only radiation. We should also keep them in mind. And here, when you have a special plate with insulation behind and receive sunlight, let's say the heat transfer coefficient is 50 watts per square meter Kelvin, and the sun reaches with a value of 7 watt square meters. Here the sun is absorbed at a value of 0.6, and there is this compound heat coefficient. And when the environment is 25, then there is this situation of balance when the plate reaches 33.4, with the heat gained being equal to heat lost. That's why the color of the external facades of the buildings matters a lot. Let's say the absorptivity is 0.9, so 90% of the 100 watt per square meter is absorbed. But in this case, the absorption will be only 0.45 with a light colored wall. I mean, in winter, absorptivity is well, but in Antalya, lesser absorption is better. So we need to, we can actually play with colors and check them. Majority of things depend on temperature measures. If you are open to environmental surfaces, and if actually there is a heat difference here, then the fluid actually temperature, then you will encounter errors. So here there should be an equality between the loss and gain. When we equalize them with the preservation of the heat, and here you see the radiation effect. That's for an example. When H is 80, let's say it reads like 650 Kelvin, and the walls have a value of 400 Kelvin, then the radiation impact creates a 65 degree difference. That's why sensors are sometimes kept under protection to preserve it from the environment. What is another method? Infiltration. Regardless of how protected your house is, air actually permeates. Let's say it's -10 in winter, and you have 22 degrees inside the home. What does that mean? In windy air, especially, that air will get inside, and it should, of course, leave the house somewhere. But actually, it goes outside the home at 22 degrees. So enters the house at -10, and leaves the house at 22. How will we compensate it? Through the heater. That's why this situation should be smaller with the window openings, wall openings, and other areas. Actually, sometimes they make the biggest impact. You may have a very well insulated wall or roof, but if your doors and windows are not that well, then that warm or heated air leaks through your house. As for the thermal comfort, I will make this last remark and finish my presentation. The human body is like a machine indeed, continuously producing heat. What is our normal temperature? 37. And generally, the temperature outside is lower than that. If we considering we continuously produce heat and cannot emit it to outside, then we will die. I mean, if it goes all the way to 38, 39, 40, 42, our body will not be able to endure it. We will feel at least unwell. That's why we should be able to comfortably emit it to outside with normal clothes if you're not covered with blankets and such. So what is the normal value? 23 degrees, 50% Q value, air circulation of 15 minutes per minute. Under these circumstances, majority people feel well, and this is called thermal comfort. What does thermal comfort depend on? Most importantly, the heat, then humidity and air speed, clothing insulation, and our metabolic rate. For example, you do exercise, you use machines, or you do wrestling with a mate, or you dance, and what does happen there? Your body will generate excessive heat, and that heat needs to be removed, and we need to have the conditions for that. Here you see actually the heat emitted from the body. Actually, an average human body has a size of 1.8, let's say, square meters. So even as we're seated, we emit a heat of 100 watts. If we talk about two fast dancing individuals, that will be more than 1 kilowatts, providing heat to the room. So you may need even air conditioning, even in winter, under those circumstances. The radiation impact and this comfort environment actually takes us to an average degree of 20s, and let's say the humidity is around this area, and this is the comfort zone, and we try to keep the interior interior temperature as such. I will finish here as we are running out of time. I can take your questions if you have any. We do not have questions about this part. We have run out of time. Many people sent their greetings and they thank you because today our professors are also watching us and they sent their greetings. Thank them. I thank them too. Well, I have made a lot of notes with valuable information. It was very enjoyable to listen to you again. Thank you very much for your contributions on behalf of all the participants. You will be able to see the comments on YouTube with them originating from Şanlıurfa, Diyarbakır, and other cities. It is 3.5 in your location. I do not mean to keep you there a lot. We'd like to thank you on behalf of the Zero Build family and on behalf of our audience. Thank you very much. I send my greetings to everyone too. I wish you a very fruitful event and I congratulate you for creating this awareness and bringing together many experts. It is great that you enable students and teachers to ask questions and get such a service. And I wish all the best to our teachers as I thank you. Thank you, Professor. We look forward to seeing you in another event. Take care. You too. Bye-bye.